And we're live, not Memorex, live. Today, most of the day is going to be devoted to getting all the programming assignments to a point where you understand what's happening and able to complete them pretty quickly. We'll have a quick review on functions. And this will work. And I thought this was, I did a search on functions, both logical and mathematical. I thought this one in the upper left, or almost the upper left here, obviously this is a predicate up in the top here where we're talking about two sets, y being an element of one set, x being an element of another set, and we're saying there exists some x squared such that for every y in whatever set it happens to be, there's an x that when x is squared, it's equal to y. And that's either going to be true or false. As a predicate expression, we like to say, okay, what does that mean when y is negative? What's y coming from? Is it a real number? Is it an integer? Whatever. We don't know because we haven't been told, but we know that once our sets are defined for the variables that we have in the predicate, at that point, this expression evaluates to either true or false. So not too bad. But I thought this one was kind of neat, where you're taking a binary reference and then you're getting arbitrary values out of some sort. Alpha could be a function. It could be a sound that you make. It could be who knows what it is. An action that's taken by electronic devices. It's simply an output that's defined as being something there. And then, of course, we have the usual kinds of things down here. This looks like I don't remember what kind, it's not quite a sign. I don't remember what kind of function does that, and it's not telling me there, so I'm just going to ignore it. Well, it looks like that's a different. The only definitions we have are in the middle here. I've got linear, nonlinear, rational, and logarithmic. The rational, for whatever reason, they didn't put a function with it. They did with the other three. The rational just means 1 over x, some function that contains 1 over x is a major part of it, so you could be adding or subtracting or doing other things. So we've got a linear, we've got a nonlinear general function here, similar to the thing on the top there. And then we've got this one. Is this a function in mathematical terms or in the terms that we're talking about? No, because 0 has 2 values. Every point has 2 values over the domain -3 to 3. We're looking at the circle for those of you on the that can't see me. But every value from -3 to +3, not inclusive, has 2 values associated with it. So as a result, it's not a function. We could take either the upper arc, or the lower arc, or you could probably argue. Well, it'd be kind of difficult to argue, but you could have intervals in there. Every tenth of or not tenth, thousandth, millionth, a billionth of an integer. Each increment of a billion changes from the positive to the negative part of the function. So if you were drawing at this scale, it would look like it's not a function, but it all depends on how you define what's going on. And there are actually formulas that would give us the ability to do that. And that's really the only thing here. Functions are interesting. We use them in a lot of different ways. We use them for simulation. We use them for translation of. We use matrix operations, for example, in graphics, using functions to determine how much light, what kinds of intensity you might have, what hues you might have in terms of the reflections or change of things. So your graphics card is doing a heck of a lot of computation, but it's usually discrete computation, integer-based computation, and modifications to an array of values that happen to be there. So kind of interesting how we do all that. We don't think about it a lot. We think math and computers are really different things. Computers are really just looking at the discrete application of mathematics and logic to whatever values we're representing in different places. which is why we have a discrete math class. And the reason computational structures. And the reason it's computational structures, I think I've mentioned this before, is because if a math teacher or a math professor was grading you on everything, it wouldn't matter. It wouldn't matter if you had the right answer if you had the wrong form or if you left something out somewhere. So, as a computer scientist, we're really more interested in outcome and in the ability to recognize and solve specific problems, not in making sure that the problem that you come up with on a piece of paper matches exactly the form of a mathematical proof or other things like that. So let's get going. Our topics, quick review of functions. We're going to take a look at our next program. And actually homework 4, which I didn't realize I'd made due 2 nights ago. So if you haven't done it yet, we'll have an opportunity to look at it and talk about it. And then we'll have some time for you guys to work on things. You can stick around if you want. You can go out and grab something from the Starbucks over in the science building, whatever you want to do. We'll take care of it. So a function, subset of the Cartesian product of 2 sets. What's the Cartesian product again? For if I have 2 sets?
Cross product.
The cross product, yeah. And that means
Each term in one set.
each term from the first set combined with each term from the second set. So if I have a set with 200 elements and another set with 200 elements, how many elements am I going to end up with in my cross product? 40 no. So that's the kind of thing that we're looking at. Is it blows up pretty quickly, but it's multiplicative. It's just, it's like looking at a matrix where each value, we could have rows for each value that's an x value and columns for each value that's a y value. And in fact, sometimes that's how we represent functions. We can call it a mapping or a transformation. The idea is that we take an input value from the first set, and that we have something that transforms it or maps it or produces the second value. It could be something as simple as just stating flat out, 1 goes to 7. It doesn't have to be some kind of formula or anything. It could just be a list of values from the cross product. But it has to be the cross product. The only thing here is that the sets have to be non-empty, and no matter what you do, every element of A has one and only one element from B that it maps to or transforms to or that it is paired with. So if you were to represent this as a matrix, out of my 40,000 element matrix with my 200 by 200, how many how many things would I end up with in my function definition for a total function? Or a function. I'll define the word total in a second. If there are 200 things in my domain, how many, and I'm representing it as a matrix, how many elements would I have? 200. Every element of the domain is mapped to something. I mean, it could be 200 possible values, but it's mapped to something. So I'd have 200, because I've got 200 in my domain, and that would be all I'd have. So if I had a matrix, it would be what's called a sparse matrix, where I could have 200 here and 200 here, and all I'm looking at is 200 dots or ones or something in my matrix that says, oh, this X element here is related to this Y element here, and I know that because I've got something in that entry in my matrix. So matrices are sometimes used, especially for small domains and ranges, but once you start getting big, like if I had 1 million elements, I've now got a million by million, that's 1 trillion possible values. That then ends up being somewhat wasteful of space. So as a result, we find other ways to represent the data at that point. We write it as function of A is equal to B, and everywhere defined is one of the terms that we use, and I've got that another slide as well. And if it's not everywhere defined, we call it a partial function. The other term that is used is total function. So in general, if somebody leaves the word partial out, they're implying that they're talking about a total function. But as we know, sometimes people will even leave that out, or will say, the function 1 over x. Well, it's not defined somewhere. A is the domain, B is the codomain, and actually the more common term for it is range. You probably heard domain and range in high school when they talked about this. Possibly even in calculus, if you took calculus, they would use the words domain and range as the main way of doing it. Though the technical term is actually codomain. We can represent a function as a list of ordered pairs. We can also use pictures. Pictures are nice, but once again, once you start getting big, what if I had like, I don't know, 20 elements in my first thing, and like 20 in my first set, 20 in my second set? My picture would start getting a little busy at that point. So pictures are useful for conveying a lot of the concepts in terms of onto, one-to-one, that kind of thing. But once you start getting to sets that have reasonably sized cardinality, reasonable means like, okay, we're talking about the students at the University of, or at Weber State University. How many students are there on campus? I don't know the exact number. It's in the 20,000s. So there are roughly 20,000 to 30,000 students enrolled at any given time, or degree-seeking enrolled at Weber State. So 20,000 becomes something that drawing a picture is not realistic at that point. So you start finding other ways to represent them. Sorry, wrong arrow. In general, we won't be lining them up when I've got sets, once again, that are, if I had 20,000 elements here, it would be ridiculous. We'd be here all day just trying to put the 20,000 elements in the first column, and we'd never get what the relation was to begin with. But once again, we use pictures to kind of represent ideas and concepts that we can then plug into the computer and make things happen. So if, for example, I wanted to talk about the composite functions where, I've got 20,000 in the first set, 20,000 in the second set, and 20,000 in some third set, I could make that composite fairly easily in a computer, but I could represent the idea of what the composite is by using diagrams like that. Okay. We can use formulas. We can also use matrices. Once again, matrices aren't common because they're wasteful. Formulas are probably the most common way of doing it, depending on what we're trying to do. F of x equals 3x plus 2, as we know, it's a linear function. And then we have some special functions that we use. We talked about floor and ceiling. Rounding, so anything that's half or more, we raise to the next power. And then the properties. And these are the things that you're going to be looking at in the next programming assignment. So one-to-one means that every element of the range, every element of a codomain, the range, has at least one element of the domain that maps to it. So, and I'll give you a shortcut. If you ask me, we'll talk about Program 5. If you ask me, I can walk you through some of the algorithms for doing these fairly easily. The one-to-one is actually not too bad. There are a couple of ways to do it, and we can do it pretty well. Onto is a little bit. For every b, if f goes, so b only has one element that maps to it as if it was multiple elements. Onto is the one I was thinking of, where for every b there's at least one a, as opposed to, well, maybe somebody's left out in the cold. If you were to ask people where they wanted to go for lunch, there might be 20 restaurants near the university. There are probably a couple of them that wouldn't have very many people say, I want to go to lunch there. So they wouldn't be considered, or they wouldn't be covered. In an onto case, somebody would go to lunch at every one of those restaurants. So that would be the concept, the kind of the real world analogy there. And then bijection is one that is both one-to-one and onto. In other words, every A maps to a specific B, so, and B only has one A that maps to it, and every B has an A that maps to it. This implies something about the size, the cardinality of the sets. And what is that implication? Each A maps you to a unique value of B. In other words, it doesn't map, no two values of A map to the same value of B. And every B has at least one value of A that maps to it. So as a total function, we're doing what? Using every value in the with the D domain. So total function means every value in the domain is used. Onto means every value of B has an A that maps to it. And one-to-one means that not only does it have a value that if it has a value that maps to it, then that's a unique value. So in other words, I don't have, let's see, we could, let's say that we have two sets. One set is the set of people in this building, and the other set is people taller than 5'5", shorter than 5'5". So we get every value of A mapping into one of those. Everybody's going to be either taller or shorter than me, or exactly. We could say taller than or less than or equal to 5 feet 5 inches. So if you're 5 feet 5.001 inches, you get to go into big boy or big person's group. So we would have the ability to say everybody's going to go somewhere. So we have onto. Because we've got people that are taller than 5 feet 5 and people that are shorter than 5 feet 5. So that would be an onto function. Is it one-to-one? No, because there are multiple people that are 5 feet 5 or shorter, and multiple people that are taller than 5 feet 5. People that have laptops with them. Well, we could talk about people in this room. Well, actually, you may have one in your in your backpack. I can't tell. But we could have two sets. We have people in the room. Do you have a laptop with you or not? Is the question that we'd be answering. And that's, once again, I've got a set A with 6 people in it, and I've got two things in set B. So set A is bigger than set B. That doesn't necessarily mean that it's onto. It simply means that set A is bigger than set B. So we can talk about the sizes of the sets, but think of it this way. If I have one that's onto, that means everything in B is taken care of. And if it's one-to-one, that means everything in B has exactly one thing in the domain that maps to it. So if I was to then talk about the sizes of set A and set B, if both of these were true, one-to-one and onto, what must be true?
Sizes are equal.
They're equal. The cardinalities of the set have to be equal to have a bijection. So the cardinality of A other words, and that's true for a bijection. So the cardinalities of the set have to be equal. Now, when we do our programming assignment, we're going to have A be the set 1, 2, 3, 4, 5, and B be the set 1, 2, 3, 4, 5. So because we have that known condition, then it makes it a little bit easier to check some of the things that we're interested in. Other terms, this is where I modified my slide and forgot to do something to it. Very quickly here we will. First we'll change that. And then, oh. Now you didn't see what the other hand was doing here. So invertible will kind of think you will probably see it on a quiz or exam. One of the things that you may have noticed, and this is true in a lot of the theory and concept classes, is that while the programs that we write are related to the things that we're talking about, we don't have programs on everything. So in other words, we may not talk about in a programming assignment whether or not a function is invertible. But we might still see it in a quiz or something like that. So invertibility is something that you might need to know about. It basically means that if I can create a function that takes B as an input and gives me A, something from set A, and it's a function, then that would be an invertible function. So I start with a function that converts A to B, or maps A to B, or transforms A into B. If I can do the opposite and write a function that takes a B value and maps it to a unique value of A, at that point we say that the function that takes A to B is invertible because I can produce a function that goes the opposite direction. So, and to do that, we have to have a bijection. We have to have that not only is it one-to-one, but it's onto. Unless we just wanted to have a partial, a partial in one direction or the other. But in total, if I'm talking total functions, then I need to have going both ways. And that's where the total function, a total function is basically a function that's defined for every value in the domain. So total is the word. You won't, I don't believe 2899 talks about the word total as a term. I do know that some of the textbooks that are used by other professors don't differentiate between total and partial functions. I think it's important because we deal with partial functions all the time, where it's not defined for some values of the domain. Normally what we'll do is we'll just say, oh, that's not part of the domain. We just kind of take that for granted that if it's not defined there, it's not part of the domain. But we're really talking about a total function at that point, or I mean a partial function at that point.
So would you just assume that if it just states it's a function that everywhere is...
Everywhere defined is the assumption that you have.
Okay.
We will, for our programming assignment, we are checking to see not whether it's total or partial. So what we'll be doing is, whether it's total or partial, we will be looking for the properties of the function. Obviously, if it's a partial function, if we only define something on half of the domain, and the domain and the range are of equal size, then it's a partial function. And at that point, we can't have it be onto. But it could still be 1-to-1, meaning that for every value of A, does it go to a unique value of B? But by default, we assume total unless it's stated otherwise. Let's see, but for every x element of the set x, there exists a y such that f of x is equal to y. And that would be totally defined, a total defined, where it's for everything in our domain. One that is not, once again, our inverse function. I could change the 4 to 8 or 16 or 27 or whatever. I don't know if 27 would work very well. And at that point, I would be taking the values of real numbers, and not all of them would map to the particular values that we have. Where, let's see, I left that out here. Oh, yeah, y is the element of, and y is real numbers. It would only be defined for certain values. Because, well, in this case, it's not defined for 0. If it's not everywhere defined, we call it a partial function. A lot of the things, especially since we're working with discrete math and we're trying to talk about real values, how many real values can we represent in a computer with a 32-bit floating point? It's got to be less than 4 billion, because there are only 4 billion some odd possible bit representations at that point. So once you start looking at exponents and everything else as being part of it, you're still limited in terms of how many things you can represent. So everything that we do in the computer is always partial. If we're saying, well, we're working with floating point numbers. Well, actually, we're working with floating point, not with real numbers, I guess is kind of the thing there. So perhaps we could draw that distinction and say, well, floating point is just those things we can represent in the computer, as opposed to a floating point being a real, which is a number with a fractional part. Even if we go to double precision, what do we get? I've got 64 bits, it's a lot more numbers, but I'm still limited. I mean, my exponent is 2 to the 11th at that point, or 2 to the 11th. 11 bits. So my exponent's 11 bits. I'm limited at that point to, what my maximum value is and what my minimum value is based on my ability to represent the exponentiation of any given number. So there's a maximum and a minimum that I can represent in the computer at any given time. So even with integers, I can't, one of the things that we do, yes, in this class, teaching 4 classes this semester is really a challenge in remembering, is it this class that we do this in, or is it, later on what we're going to be doing is we're going to be counting things. And what we'll find is that there are some things we can't represent directly in the computer unless we have a special math library that allows us to represent bigger numbers. So it's kind of interesting. What I have you do is I have you count the possible ways to, COVID vaccine is coming again. I don't know how many people are going to take it now, but the government's pushing it, and I had never heard a pharmaceutical company advertise as broadly as they did following the COVID lockdowns. So both Pfizer and Moderna have been, it's like every time you turn on a streaming station or the radio or something else, there's Pfizer, yes, you have to be vaccinated. Anyway. But what I'll have you do at that point is say, okay, I've got 8 doctors 12 doctors and 36 nurses. How many possible ways can I administer doses to them if I break them down into 3 groups? Because with an emergency room and people potentially having a reaction to a vaccination, you wouldn't want to give everybody the shot the same day. The next day, nobody might be able to come in. So instead, what you would do is you'd say, okay, we're going to break it down, and the number I give you is over 3 different groups, but we count that, and what we find is that the number of possible ways to break them into 4 doctors at a time and 12 nurses at a time, the number of possible ways to do that is so big, we can't represent the number inside our computer. Just as an aside. So every time that we're talking about things in the computer, we're limited in what we can represent. And we have to do special things. For example, to compute pi to 100 digits, what do you have to do? Well, you need a special library because the hardware itself, generally speaking, will not be able to represent that. At least not directly. And then finally, our composite functions, we looked at this last time. It just means that I figure out what f of x is, and then I plug it into g. And that gives me a value of from the second codomain, or the second range. So we have whatever's on the right of the circle is the things that's applied first. So, and if I have a bunch of them, then I'm just applying them in order. So if I had 4 functions there, if I had I of new, oh wait, no. Sorry, that's from the witch's manual, not from the functional manual. But if I had 4 functions, then all I'd have to do is make sure that one function maps to the domain of the next function, and then that function maps to the domain of the third one. So the codomains are the domains of the enclosing function is really the only thing that we're talking about. All right. Before I get into stuff, do you have any questions on any of the programming assignments that we've done up to this point? I'm a little behind on grading. I wanted to be about a week ahead, and putting this computer into a state where I can actually use it has been a bit time consuming, but I think I finally got it where I want it, and I can start grading again. I've got about 100. When I checked 2 days ago, I had about 100 programs to grade. So I've probably got a few more now, because that was Tuesday afternoon I checked. But it's fun. 5 different programming languages, over 4 classes. If you want assembly language, I'm not grading any x86 assembly, not this semester. I've done it, but not this semester. So do you have anything right off the bat? I have, I'm trying to remember, I believe I've looked at some, I haven't graded any that did string ones. I have given some help on those. So if you look at the notes from last time, hopefully that will clarify things. Let me reemphasize, you must use integers. Don't use sets, don't use arrays, don't use, C has a bit set, which is kind of an interesting thing that you could potentially use. Don't do it. Don't do it. Essentially what we're doing is we're doing bit sets on our own. But we're limiting ourselves to integers. We're not just randomly going in and saying, I'd like 10,000 bits, which would be something you could undoubtedly do, but you're restricted to the operations that they have there. So we're going to brute force our way through, in part just so that we know the difference between, we know what's going on under the hood with bit set at that point. Well, we know partially what's going on. So if I had 10,000 bits that I wanted, what would I have to do? It would depend on the underlying architecture, but in general, I have to go out and grab a section of memory with 10,000 bits in it. So 10,000 divided by 8, that's what, right? and 1,250 bytes. And then I've got to find a way to put them all together into a single piece of memory. So if I want bit 5,000, I then have to figure out where bit 5,000 is. Well, it's going to be offset into a specific byte in that range, and then I would pick that specific bit out of that byte in memory. So we could, for example, represent that as an array of, we could either do an array of bytes or an array of integers. Either one would work. Does that make sense? Let's say that rather than 9 values, I'll use the string here. Okay. So, using more than 10 bits. So with 10 bits, it's pretty easy. I just need, at most, I need 2 characters. But let's say that I wanted, 10,000 might be a little much. The math, doing the math in my head might be a little difficult there. Let's say that we wanted, let's say we wanted 1,000 bits. Well, what's 1,000 divided by 32? Maybe I should do this in my 2420 class. This would be an interesting exercise. I have my 2420 class do template types, which is what a bit set is. It's a template type where you have to give it a size, and then it implements it for you. Yeah, here we're. The only thing is that it limits itself. Unlike an array is a template class as well, where you have to define the type of thing that's stored. But here, you're just defining how big it is, and then it represents everything as bits in the machine. So a little different template in that the only thing we're providing is an integer size, where with a lot of things, like with an array or with a queue or with a DQ or a vector or anything else, we're saying, not only do I need a certain number of these things, this is the type of thing that you're storing in it. Sometimes it may be dynamic, it might grow or something like that, but yeah, it would be interesting to have my students do this for me. Anyway, 1,000 divided by 32. See, if you guys let me go, we're going all kinds of places. You may learn someday just to ask questions. If you don't, then you have to put up with my ramblings. Okay, so, darn, I don't have a numeric keypad anymore. Divided by 32 should be 3 something. Oh, 31. So I need 31 integers. Equals 31. Is it really that exactly? Or am I in some kind of weird... Oh, I'm in the programmer thing. So, so if I change the scientific... You get integer division in the programmer calculator. 31.25. So I need 32 of them. So I'd have 3 bytes of the last integer that I wouldn't do anything with. Does that make sense? I'm not hearing anything, so I'm going to assume that your heads are nodding up and down and saying, actually 31.25, so we need 32 inches. At 1, at 2, at 3, and in our last one, we're only going to use the first byte, the other bytes we're not going to use. So that's kind of the way that it would happen. What we could do for our bit set is then, if somebody comes in and says, we want bit. Give me a number. So we're at something between 1 and 1,000, 0 and 1,000, or 1 and 1,000.
18.
18? Yeah, I guess that'll work. So 18, what we do is we'd say, all right, what is, let's see, since we're using it as an index, we probably want to use the floor. So 18 divided, pardon me. So 18 divided by 32, and we do the floor function for that, and that would be equal to 0. So this tells us which integer so that would be this one, integer 0. And then we want the bit 18 out of it. So we would then do a let's say that this is an array, my bits of 32 integers. I want my bits floor of 18 divided by 32. I'm not paying attention to which things I want, and then I would and it. So are we starting numbering our bits from 0? Or are we starting from 1? We're just saying we had 1,000 bits. Do we want to index from 0 or 1?
0.
Okay. So, and we'd AND it, bitwise AND, with 18 minus 1. So, okay, that means that if we say 18, we want the 18th out of 1,000, or it's bit 18 starting at bit 0. We'd have to make that decision. That would be that's the only catch here, is once you start implementing something like this, you have to decide what it actually means. But this would get you to whichever integer. Like if I want 500, 500 divided by 32 is going to be about 16. So we'll go to the 16th integer, and then we'll select the appropriate bit within that integer, and that would give us 1,000 integer or 1,000 bits to represent data with. So we can do it. We don't need the library that somebody else wrote in C++ or Java or something else to do it. So I guess that's kind of the expansion of what we've done so far is just understanding we're really capable of doing it. It's not, we don't have to rely on something somebody else did in order to make it happen. All we need is our arrays, built-in feature, it's in standard, and the ability to do bitwise operations and simple math. And we're all set. We would probably need a math library for the floor function. I don't think I don't remember if that's included in standard or not. So that's where we just need to program in the language a lot more. How many of you actually have the reference for C++ or some kind of book or something that you look things up in, or Stack, what is it, Stack Overflow, that gives you an answer that's correct maybe 40% of the time? When you're programming, I mean, I don't know about you, when I'm programming, especially this semester, I've got 5 different languages. I don't remember all 5 languages off the top of my head to the point where I can debug, but trying to sit down and write solutions in each one of those languages in every class, I have to have a reference. In my 2810, my assembly language class, I use the help in the interface all the time, because once I start typing a command, it'll show me all the different formats, and then I can choose what I want to do at that point. The more you learn, the more you're going to need a reference, is essentially the point I'm trying to make. That nobody, unless it's the only language you use and you use it day in and day out, nobody programs without some kind of reference. And even the person who programs day in and day out is usually in a rut. They're in a rut is probably the wrong word. They're working on specific things within a language, so if you push them outside of that area into a part of the language that they don't use frequently, they'll probably have to look it up. CPP reference or something like that, where they will go out, they'll look up how something works, and they'll figure out how to solve the problem. So the abstraction, the idea of having a whole bunch of bits is really what we're interested in. It just becomes a question of how do you do that. So if I was doing this in assembly, MIPS assembly, what I can do is I can actually go out and grab 1,024 bits or bytes of memory. Or in this case, I would need 1,024. I'd need, let's see, so 125 to get 10,000 or 1,000 bits. So I can get 125 bytes, and then I can work from there and use an index into those 125 bytes and access that byte directly using the address. And so there are always ways to do it. It's just within specific languages, the method that you use is going to vary. Okay. This is tongue-in-cheek, but maybe there aren't always ways you can do it. I'm not sure that Java would work really well with this. You'd have to do an array of integers and stuff like that, but you could still do it. You wouldn't be able to use pointers and other stuff like that, but yeah. Anyway, let's go ahead and take a look at other things. We do have another programming assignment coming up. It's properties of functions. We're going to be looking at that, and the working with arrays. Since this one was actually due 2 days ago, let's go ahead and take a look at that one first. Okay. Do I want? Okay. I just made Chrome my default browser. So here, I've changed it a little bit. I added a little discussion at the beginning of this. I probably should have done it before. I didn't realize it was due the homework was due this week, because it's not actually even in there until this week. So I'll change the due date. As you know, the due date is not a vital consideration. But we've got 2 parts here. The first one's just using an array of integers. I give you an algorithm for bubble sort the integers. Life is good, print them out. Read in 10 integers, type random numbers in, sort them, and hopefully they'll be in order. So we'll use bubble sort. It's an n-squared sort. We're going to make it a little bit better than that, but not much. You can't really do too much. And let's see. So our algorithm for bubble sort. All bubble sort does is it does a comparison. So essentially you start with, you have your array of integers. Let me erase that. We're not talking about sparse matrices anymore. So I've got an array of, let's see. Now we can do 4. So let's say I have an array of 4 numbers that I put in. All this algorithm is doing is it's saying, okay, I'm going to look at this element, and I'm going to compare it. So I'll compare. This is A, B, C, and D. And I don't know what the ultimate result is going to be, but essentially what I do is I compare A with B, or actually I'm going n minus 1 down to 0 to n minus 2, and n minus 1 down to. So I compare is AJ, so the last element in my array, or less than A sub j minus 1. So actually I start at this end. And I compare D less than C. And if it is, I swap. If so, we swap. And then I compare whatever the result was, like if it was, then I compare these two, and then I compare these two, and at the end of that, what do I have? That first time through the inner loop, this is the minimum value. So that's this inner for loop, j equal n minus 1 down to I plus 1. So what I'm doing is I'm finding, the first time through, I'm finding the smallest value. If this one's less than that one, I swap them. If that one's less than this one, I swap them. If that one's less than this one, I swap them. So I've swapped the smaller value all the way down, and I put the smallest value here. And now I just start on the rest of it. And I do the same thing over and over and over. So basically, I look for the smallest one, I look for the next smallest one, I look for the next smallest one. And I'm just moving the smallest one to the next position. So this would be the second smallest one, and then I'd have the third smallest one, and then I finally, which since I've got all of them, I'd pretty much be done at that point, and I had my 4 numbers sorted. That's all bubble sort is doing. It's just it compares everything with the goal of only finding the minimum value, and then it says, okay, this part's done, now I'm going to start on the rest of it. But to do that, as you can see, the outer loop here, we're not going to be doing a lot of analysis in this class, but we do talk a little bit about algorithmic analysis and growth of functions. Here, I've got an n on the outside, I've got an n on the inside. So this is an n, what would be called an n-squared algorithm. So I have to do n-squared comparisons or something on the order of it. It's a function of n-squared. It's not exactly n-squared, it's a function of n-squared. So I'd have to do n-squared comparisons to make this work. But it's not too bad. If you have this did swap comparison or Boolean in here, all that does is it allows you to finish early. So if, for example, everything was sorted except this was the smallest value, but the rest of these were in order, all did swap does is it'll move D all the way to the beginning. The rest of them will still be in order, the order that they were in, and did swap the next time through it'll say, oh, I didn't move anything, I'm done. So in other words, if I do a comparison and I'm not swapping anything, then there's nothing to do beyond that point. And that's all did swap does. I've got an example here how you can put it into the outer loop as well. We only use it here on the inner loop with the if statement. Or actually, no, that's if did swap is false, then break. No, that will take us out of the outer loop. I normally would prefer to put it in here, but you can put it in as a break in the inner part. Just as a one way to do it. But it's pretty straightforward. You do not have to declare. I am not requiring that you have dynamic arrays where you say, okay, how many elements do you want? Okay, I will allocate. You want 25 elements. I'm now going to allocate an array of 25. If you just want to put in, I'm not going to have any more than 10 or 20 elements. That's fine. You can test it with as few as 2. Actually, you can test it with 1 element and see if it crashes or not. It shouldn't crash with 1. But that's all this one is just a very quick way of, or not quick, but it's an easy way, usually an easily understandable way to look at putting things into order. And that's really all we're going to do there. Because we need to be comfortable working with arrays, and integers are pretty simple to work with. The second part here is one that you probably have never done before. It's the idea of using characters to index into an array. As you know, in Java, C++, C, our indices always have to be numeric values, 0 through some number. All this does is it says, okay, I know that the characters that I have in my language come from some encoding. What encoding do we use for characters in most of our programs? ASCII. So we usually use the ASCII encoding, and those are bytes with a bit representation in there, and a byte is a numeric value. And that's really all we're taking advantage of down here is the idea of having using the numeric value of a character to determine something. So on our input characters, we can loop through every letter. So for example, if I have an input string, Java, C++, Python, doesn't matter, I can use an index in here. That will get me a specific letter. In Java, I think it's char at or something. It's something weird like that. But in most of the other ones, you can just treat the string as an array of characters without too much difficulty. So here, I would have an array of integers indexed by what I want to index by is, or I'm going to use it to count the number of characters. ToUpper converts the character here to an uppercase letter. So if it's lowercase or uppercase, it won't matter. The reason I do that is what we're trying to do in this program is we're trying to say, okay, how many A's are in the input string? How many B's? How many C's? So by converting everything to uppercase, then I don't have to worry, did you enter a lowercase b or an uppercase b? And that gives me the ability then also to just subtract a capital A from it. So if the character that was put in, let's say the character is a lowercase a. When I convert it to an uppercase a, then that's what my ToUpper does, and I subtract the letter from it, what do I get? What's 1 byte minus another byte?
0.
In this case, if it's capital A minus capital A, I get a 0. Luckily, capital B comes right after that, capital C comes after that. The first the 26 letters of the alphabet, the capital letters, are all right next to each other. They start at ASCII 65 and go up from there. The uppercase, the lowercase letters come later. They start, if I remember right, it's 97. for lowercase a. So by converting to upper, I don't have to do the, okay, there's like 10 characters between the uppercase and the lowercase characters. We have to worry about whether or not we have a semicolon. Oh, no, a semicolon comes earlier. I don't remember what the characters are between them. But there are a few. It's not all the capitals and then all the lowercase letters. So this way, we really just want to know how many A's there are, how many B's, how many C's. You might do something like this if, for example, you were doing some code analysis on somebody's encoding of a message, or frequency analysis for letters for language purposes, where you might be looking at things. And so that's the kind of thing that we might be doing here. But here's an example. If I put in the string Bob is a palindrome, which it is, then what I would expect is, well, I've got two B's, so I get a 2 for B. I've got an A there and an A there, so I've got two A's. I've got a D. I do not have any C's. And that's really all we're doing. We're just saying, okay, I'm going to initialize every value of my array to 0, and then loop through, 0, 1, 2, 3, loop through all the characters in the string that are read in, and if it's an alphabetic character, I'm going to count it. That's all our program should do. You will be using this later on in the semester. The very last program we do, we're looking at a finite state machine, and basically it'll be a machine where we we enter a key and then we encode a string using that key. And to do that, we'll be using characters as indices into our key. So if you type in an A is going to go to another letter. Has anybody in here ever done a cryptic quote? It's like, we'll see this later in the semester, but I might as well do it now. We've got a little bit of time. Not too much anymore, but we can just, let's see. So this is Arkansas Democrat. Essentially, all it is, it is what would be called a replacement cipher. It's a simple replacement cipher. We have a key up here that says that L is replaced by A, O is replaced by X, N is replaced by Y, G by D, and so for each letter we have a letter that replaces it. The most famous of these ciphers was the Caesar cipher, and that was a rotational cipher where all he did was shift things 3 letters. So he could write it down just directly. He didn't have to remember, well, A goes to P and B goes to, I, or something like that. If you do just a shift, it's a lot easier to solve, because then all you have to do is remember it. But this is, as a crypto quote, it's not direct. So just because L goes to A does not mean M is going to go to B. And that's the whole idea, is that you're hiding or you're encoding something to make it difficult. So here, how many words have 1 letter in them? 2. So F is either A or it's I. So because we're using English, we can tell that right away, and then W would be the other one. One of them's I, one of them's A. We don't know which one is which until we start replacing other things. And then you get 3 letters. Let's see. Yeah. Double letters, you're probably not going to have a double Q anywhere or stuff like that. So you could, as a human, we would look at that sort of thing. But what we'll be doing is we'll be writing a program that will allow us to create a crypto quote, or to enter the character replacement that we think will solve it, and then see if it solves the crypto quote. So that's our final one, but we're basically using a finite state machine that says I start in this place, I get a character in, I'm going to do something based on the key that you enter. I thought it'd be a kind of a fun assignment to do that sort of thing. So let's take a look now at our other keys here. I don't know if you've looked at the properties of functions yet. Essentially, we are writing a function. We have a set A and a set B that are the same. 1, 2, 3, 4, 5. I need to add Java as a language here. You can do this in Java as well. Change my. Okay, domain and range respectively. We'll accept partial functions as valid here. So if I only enter three pairs, it would still be valid. It could be one-to-one. We know that if it's only 3 pairs and I've got 5 things in my codomain or my range, is it onto? What's the definition of onto? Every value in the range has, there exists a value in the domain for every value in the range, such that f of the value in the domain is equal to the value in the range. So if I only put in 3 ordered pairs and my range, or pardon me, my codomain, my range has 5 elements in it, will I ever cover all 5 of them? No, I can't. So if I only enter 3 ordered pairs, obviously it's not going to be onto at that point. We're not going to worry about onto for the ones that are actually there. No, it's the range. The range is always 1 through 5. But we will accept partial functions at that. For one-to-one, and at that point, it's just a matter of for any value of x that has a mapping, since it's a positive, a partial function, is it the only one that maps to that value? In other words, for the b, if there's something that maps to b, is it only one value that maps to the b value, or the y value in this case? So if f of 3 is equal to 2 and f of 4 is equal to 2, it's not one-to-one. But if f of 3 is equal to 1 and f of 4 is equal to 2, then if those are the only 2 ordered pairs that I enter, then it is one-to-one at that point. Because if I give you 1, you can say, oh, the value of x that mapped to 1 was, and you can give me 1 actual value at that point. Okay, I give you a sample program. And anybody running only on Mac, because I don't have a Mac to compile on. I can give it to you on Linux. So I can create a Linux executable if you want that, but I don't have anything else. But essentially, please adhere to this, and for my Java programmers, only have one scanner. Don't put your scanner inside the function that reads in the ordered pairs. The reason for that is my scripts that I use for grading will break. So always make your, for this class, it may be bad programming for Java programmers, I don't know, only make one scanner for the entire class. Then, or don't put it inside methods inside the class. So ask for the number of ordered pairs and then read them in, 1 pair per line. In other words, if 1, 2 is an element, then I would have a 1 with a space and a 2. I put a tab between them. Any white space will be ignored. And you can use in cin. Anybody know how to do this in C++? You guys you've led a sheltered life. Okay, let's see. C out. it'll do it. So I can enter multiple values. So in C, you simply have a scan in and you list with comma separated list. In Java, you'd have a next int, and you could actually have two next ints in a row, and have next int x, next int y, and it would be able to do that. So you can read one line and pretty easily. I will caution you, and we may run across this later in the semester, when you're mixing character input or string input with numeric input, if you read in a string and you're not reading in the entire line, it leaves a new line character in the buffer, which means that if you use cin to try and read in an integer, it thinks you pressed to enter. And it will typically just skip over the input at that point. So be aware for your programming when you're using cin in order to input either a string or a character or something like that, that when you get to integer input and you mix it with characters or strings, the integers are going to have an issue. So what you have to do is clear the buffer, and there are a couple of different ways to do that. If you do a look online, even, believe it or not, even Stack Overflow can do this correctly about 7 times out of 10. If you look for clear the input buffer, you'll find that there are several different ways to do it. They should probably add that as a method for cin, where you just have a call that you can make that will always clear it up. So what we'll do is we'll read them in and then do stuff with it. These are exactly the test cases I will be giving you. I do have one additional test case, and I'm trying to remember why I did that. I had it was in response to the way that a student did something, and I probably should add it to my list here. But they did something weird in either Onto or one-to-one, and I don't remember what it was off the top of my head right now, but I wrote a test case to see when somebody did that. But the results are here. If this is the input, this is the result. Valid, one-to-one, not onto, not bijection. One-to-one because 4 only comes from 1, 5 only comes from 2, 1 only comes from 3, and 2 only comes from 5 for the first function. You'll note that my output here, even though it's F parentheses, I'm only reading them in as 5 and 2. I'm not reading them in with F parentheses equal, parentheses 5 equal 2. If you do that, I will curse you. I have, not every semester, but most semesters I have students who say, oh, this is the sample input, ordered pairs. This is not an ordered pair input. This is a function input. The ordered pair is the first number, the second number. You could potentially put parentheses, a number, comma, parentheses, the number, and another comma. But all I want is, give me the numbers only. Numbers separated by a space. This one's not valid. Why is this not valid? I've got 1 goes to 5 and 6 goes to 4. 6 is not in our domain. So if I have values that are outside the domain, it's bad. So it's not a valid function at that point. This one, 1 goes to 2, 2 goes to 4, 3 goes to 3, 4 goes to 2. I've got 2 used twice here. So at that point, I know it's not going to be 1-to-1. So it's not 1-to-1. And because I repeated the 2, I only used 4 of the values, not 5 of the values in my range. So it's not onto. And if it's not 1-to-1 and not onto, it will not be a bijection. This one, 1 goes to 0, 5 goes to 4. Not valid because the 0 is out of my range. So if I have something out of my domain or something out of my range, I want to be able to evaluate it. Don't just kick out immediately and accept the value before you do the determination on whether or not it's valid or not. So if I type in 10 and your program stops, I'm not going to be a happy camper because I have a script that puts in all the values, the ordered pairs. I say I've got 2 of them, 10, your program stops, my script might die on me. Here, 1 goes to 5, 2 goes to 4, 3 goes to 3, 4, 2, 1. So valid, 1 to 1, because each one of the range values appears only one time, and then it's on to because all 5 of them are there. So all I have to do to check 1 to 1 is, for 1 to 1, all I have to do is check to see if I have any repeated Y values. So it's an embedded for loop similar to the bubble sort, where all I do is I start at the first one, I see is it repeated, then I start at the second one, see if it's repeated in the last 3, or however many there are, but I just loop through and check the first one against the rest, the second one against the rest, the third one against the rest, and the fourth one. So I only have to go up to 4. Yes?
Or could you just have a singular if statement, like a bunch of or conditions, just pitting each one against each other?
That is a valid methodology. But the question is going to become, how are you going to tell how many elements I've actually entered into the program as ordered pairs?
New plan. 5 different if statements, depending on how many elements you have.
If I remember, the rubric has an element for overly complex design. That would be what I would consider overly complex design, because all I have to do is with the nested for loop is I can exit as soon as it's false, and all I have to do is compare 2 elements, compare the next 2 elements, and the first one that fails, I'm done. I don't even have to compare anymore. So I add whatever Boolean it is, like is 1 to 1, and when it's false, I'm done. So I add that to the for loop. 10. So I could have for I equals 0. Let's see. Is 1 to 1 equal true? I less than some pairs. So, because you're going to tell me how many pairs you entered, or actually num pairs minus 1 at this point, and is 1 to 1. You don't have to spell it out this way. I'm writing it this way to make sure everybody understands. Okay, it'll be I plus plus. Inside here, I'll have 4 j equal I plus 1 j less than num pairs, and is 1 to 1. J plus plus. And inside here, all I have to do is set is 1 to 1 equals, let's say that I called my second value of ordered pairs my array of y values. So is y I equal y j. if they're equal, I want to set equal to false. Right? So if they're equal to each other, I want 1 to 1 to be false. And actually, I can even do, well, no, any of this is true. Because I'm going to have 1 to 1 even if I don't have 5. So is 1 to 1 equal to not that. So if it's equal, I'll get a false. When I get the false, I exit this loop. When I get in this loop and I'm done, it's false. It's not 1 to 1. Because if they're equal, I take the not of that and I assign it to 1 to 1. So that gives me the ability then to just check the minimum number of things. I have to do a loop to do it, but it's because I don't know how many ordered pairs I have coming in. And it would be wasteful to have five if statements, especially if I wanted to compare each element to every other element. Well, I've got to compare the first element to the other 4, the second element to the next 3, the third element to the next 2, the fourth element to the last one. So I'd have to have at least 4 if statements, and I'd have to have a number of comparisons within each one. So I can do it all with this, and then I don't have to worry about it. I'm doing the comparison at each point. So that'll do 1 to 1. The on to is basically almost the same thing. If it is 1 to 1, and there are 5 elements, so you can do 1 to 1 and the number of pairs is equal to 5, and that'll tell you whether it's on to or not. But our test cases, you can test each one of these. You should get exactly these values. Once you find out, the first thing you want to do is you want to check all the ranges. So you can actually set a variable as you're reading in values to figure out whether something's out of the range or not. Accept what somebody types in, don't stop. Just set a value that says, oh, there's a value out of range, it's an invalid function. That would be an easy way, as you're reading in the values, to determine whether it's valid or not for input 2 and input 4. Input 6 is not valid because there's a repeated x value. 2 goes to 2 different values. So I'd use the same algorithm for the X array. So if I read them into, I can either read them into a single 2-dimensional array where 1 column is my X values and 1 column is my my Y values, or I can read them into 2 different arrays, an X array and a Y array. Couple of things to consider. Ooh, we're almost at time. When I pass an array in Java, C++, Python, C, what am I passing? Have you ever heard the expressions pass by reference and pass by value? Maybe. Okay, what's pass by value?
Is pass by value like you're passing the individual items inside the array?
Yeah, kind of. It's normally what we do with scalar values. Like if I pass an integer, what happens is I take a copy of the value and I put it on the stack. So it now becomes the equivalent of a local thing inside the function or the method. And when the method ends, my main program variable, if I just passed a variable as a parameter, is unchanged. But I can also, if I'm passing an integer, I can use an expression. Like if I want to pass in x plus 2 as an integer value, So somebody types in X, I pass X is 2. Well, X plus 2 is not a memory location. It's not a reference to memory. So I determine the value of X plus 2, and I use that value as the parameter. Scalar values in C++, in Java, C, Python, scalar values are always passed by value, unless you indicate, I'm passing it by reference. How do you do that?
Pointers.
You specify that you're passing, you can't do it in, you can do it in C. C++ added a little ampersand before, like int ampersand and then the name of the parameter. That means that you're passing it as the reference to the memory location. So anything you do to it is going to happen to the thing in the caller, whoever called it. For arrays, what is the name of an array? What's the value of the name of the array? If I've got 5 values in the array, what value would I be passing? The answer is the address of the array. Every time you pass an array or a structure or a class object, well, class objects are a little different. Sometimes they will be, structures and class objects will oftentimes be passed by value. What it'll do is it'll grab a piece of the stack and copy all the things from the object into the stack, and then inside the method, it will manipulate that copy. But for arrays, it is always passed by reference. So the name of the array, when you get inside your method, the array name that was a parameter is exactly the same memory location as the main program array. So when you read into the array, you're manipulating the main program array at that point. So if you modify something, it changes what was in the main program. The only way to get around that is to create a local array, copy the values into it, and then change that. Yes?
For the program, do we have to use arrays or can we use vectors? Just because I'm more familiar with vectors than I am with arrays.
Vector is essentially an array, but yeah, you can do either one. I mean, you're still going to be, you're going to be doing in, and you're going to be doing some vector checking. I use arrays because I know precisely what is happening there, and I don't have to look up the method for how to get a specific element out of the vector. It's just by an index, right?
Yeah.
So essentially, a vector is an array at that point.
Yeah.
So unordered, we just have values that happen to be stored in a specific order in the array. So yeah, you can use either one. In this case, if you're using vectors or arrays, it's irrelevant as long as your program functions correctly.
Okay.
So you may use either one. Let's see. This is just some sample output. I probably need to provide some sample input, but I give you that sample program. Run through it a couple of times. Please match that. So read in the number of ordered pairs that you're going to have, and if somebody enters the same thing twice, it's fine. You don't have to do any checking to see, well, have you already entered 2 as the X value? As you know, there's a test case where that is there, and you must return that it's an invalid function. So allow somebody, if they say they've got 5 pairs, allow them to enter 5 ordered pairs, and then perform your analysis. Is it a valid or invalid function? And if it's valid, that's the only time you need to check one-to-one onto or bijection, or end bijection. It sounds really hard, but just write a short function to read in, like a 10-liner to read in the ordered pairs and store them. You can check to see if you have any values out of range at that time, and you could even return that as a return value from the read in. Actually, you'll probably want to return the integer that tells you how many pairs you have. And then your main program can have, you can have a function for valid, you can have a function for one-to-one. If it's one-to-one, you can use that in a simple if statement for onto. You know, if it is one-to-one and the number of pairs is equal to 5, then it's onto. Any questions? It's really not, I mean, it looks tough. It's like, oh my goodness, I've got to read in ordered pairs and then I've got to do different. But if you keep in mind the ability to check one element against all the other elements, you can do the one-to-one, you can do the repeated x values, the same, using the same methodology. So all I'd have to change in this particular case is instead of checking y for valid, I'd check the x values of the ordered pairs. Because if I have two x values that are the same, that means x goes to two different things. Or we'll make the assumption that it goes to two different things. So in this case, if they enter x, you know, one maps to 5 and one maps to 5, we'll say that's not a valid function. No. If you really, really, really want to add the ability to check for repeated, for the same ordered pair being entered twice, you could do that, but I'm not asking you to. So, your programming assignments are designed to take about 30 minutes to 45 minutes. So if you're spending a lot longer on it, it's time to put it down, send me an email, and say, I'm having issues with this. So 45 minutes, there's one, maybe two that'll be a little bit longer, but it's cut and paste and make sure that you correct things as you go. It'll make the correct modifications as you go through. Alrighty, you guys have a marvelous weekend. Let me check the people online and see if they have any questions, if they stuck around. You guys have any questions? You do? They're probably eating sandwiches right now. Sandwiches or burritos or nachos or shawarmas, gyros. Give me some fresh fruit. Picked up some really nice